Okay, so we're in lesson 7.2, sample proportions. So the sampling distribution of the sample proportion p hat describes the distribution in all possible samples of the same size. So like samples, like taking 20 at a time and averaging those. So each one of those p hats represents a sample of 20 that we took the average of those 20 characters, 20 things. So in this case, we're talking about samples of pennies of sample size n equals 20. So it means we took 20 samples from the population, averaged those. Each one of those times we did that, those are all those individual p hats there to make up that sampling distribution. So one thing we can do is you can almost anticipate, just knowing some of the characteristics, some of the things, you can anticipate the shape of what things are going to look like. So you look at the top middle here. The mean is 0.5. And so when the p hat, when I say mean, it's the sample proportion is 0.5. So whenever the sample proportion is very close to 0.5 or close to ish to that, you're going to find that the typically it's going to look approximately normal. Same thing in the bottom middle there. The sample proportion there is 0.5 and it looks approximately normal. You can see here in the top left that the p hat is 10% or 0.1. So that's very close to zero, right? If you think about percentages from 0 to 100%, 10% is pretty close to zero. Anytime you get a value that's close to zero, where the middle is close to zero, it almost by nature has to be skewed right there. You can see that that tends to be kind of skewed right because there's not much room on the left of 10% to kind of, spread out. It's very limited, the amount of 10% or less compared to how much you can spread out to the right. So it's typically going to be skewed right. And then here on the right, when the mean is, that sample proportion is 90% or 0.9, we don't have much room on the right, so it's going to be skewed left typically. Now it does depend a little bit, it seems like, on standard deviation. So on the bottom compared to the top, it looks like on the bottom the standard deviation is about half as big. So it's not quite as skewed right there on the bottom left, and it's not quite as skewed left on the bottom right, but it still probably is skewed a little bit there. So when n is small and p is close to zero, it's almost always skewed right. So if you're taking a smaller amount of sample sizes there, not 25 instead of 100 or something, and p hat is 0.1 there, that's going to be skewed right. When n is small and p is close to 1, it's going to be skewed left. We kind of mentioned that. It's close to 0.5, it's going to be approximately normal. So in this one, let's see. So it looks like the n value is a little larger, n is 100. P is 0.1, which is close to 0. So it is probably going to be skewed right, but it's closer to approximately normal there. Is equal to pop proportion. This makes sense because sample proportion p hat. So as n gets bigger, you're not so concerned. It becomes more and more approximately normal rather than skewed. And again, it's an unbiased estimator there. So variability. So the standard deviation depends on both n and p. So if you remember, even the formula, you derive it from that number as well. The formula involves, I think, square root of pq over n. So the standard deviation is larger for values of p that are close to 0.5. So typically when you have 0.5, you're going to have larger standard deviation. There's more room to spread out if you want to think about that way, but smaller standard deviation for values closer to the edges there, 10% or 90%. The standard deviation gets smaller as n gets larger. That's definitely true. So if n is 25 on the top, you can see it's pretty spread out. But n is 100, you're going to have more precision there, less variability, and so you'll have that. Okay. So the mean is just what you expect. The standard deviation is the square root of PQ over N, Q being the chance of failure there. That's as long as a 10% condition is satisfied. So that's very important condition to check before you do the standard deviation. Less than 10% is because we're sampling without replacement, and it kind of proves independence, or at least a semblance of independence there. To be considered approximately normal, we have to do the large counts condition, which is the NP, which is the how many successes we predict, and NQ, which is how many failures we predict. Both have to be at least 10. So we have to meet the large counts condition again. To prove normality, and then the less than 10% condition to prove that it's independent because we're sampling without replacement. Okay. Sample distribution. Suppose that 84% of students at a large high school regularly use backpacks to carry their books from class to class. Imagine taking a simple random sample of 100 students and calculating a p-hat, okay, of who uses a backpack. So identify the mean, the sampling distribution of p-hat. The mean would be 0.84. It's pretty obvious. Calculate and interpret the standard deviation of the sampling, verifying that the 10%, less than 10% condition is met. So 100 students. So for the 10% condition to be met, there has to be at least 1,000 students at the school. For a large public school, that large high school, that's probably no problem. And so we would say that does meet the verified the less than 10% condition. The formula there is, so it's square root of PQ, so 0.84 times 0.16, or you could do 1 minus 0.84, all over N, which was 100. So it should be 0.036. Describe the shape. So if we can prove that it meets the requirement for successes and failures here, the large counts condition, so NP would be 100 times 0.84. We expect 84 successes. 100 times chance of failures, 0.16. We expect 16 failures. Those are both greater than or equal to 10. Therefore, it does pass the test. It does seem to be something we can model with a normal distribution. We could always do norm CDF or whatever we need to do to answer the questions that may follow. And that's what that is saying here. Exactly true. I like the way they notated it. 100 times 0.84 equals 84, which is greater than or equal to 10. So they just kind of notate it that way. I really like that. The sample is approximately normal. That's one thing we already mentioned. And so if it does pass that condition, then we can use the normal thing. Okay. So polling organization asked for an SRS of first 1,500 first-year college students to how far away their home is. Suppose that 35% said students they attend college within 50 miles. Find the probability that the random sample of 1,500 students will get a result within 2 percentage points of the true value. Okay, so p-hat, the mean of p-hats can be 0.35. If it passes the, let's see, the less than 10% condition, so they sampled 1,500 folks, and we're assuming there were more than 15,000 first-year college students. That's safe to assume. So that's really passes less than 10% condition. So we can do standard deviation here. So square root of PQ, which is 0.35 times 0.65, 1 minus 0.35 over 1,500. So we get that. Okay, so then we can we do the NP? So it's going to be 1,500. I'm pretty sure this is going to work out times 0.35. That's at least 10 there, and then 1,500 times 0.65 is at least 10 failures. So we have at least 10 successes, at least 10 failures. We can use the normal model for this. So let's let's try to draw this. I think it helps to kind of draw this out. Oops. So the mean is 0.84. We're going to add 0.012. So we're adding, the standard deviation is 0.012 here. So, which is 1.2% essentially, 0.852, 0.864, 0.828, 0.816. I believe I did that right. Okay, so that's the standard deviation there. So within 2 percentage points, so 84 would be from 86%, so 0.86, down to 0.82, so somewhere in that neighborhood, 0.82. So kind of between those two is where the shading is going to be. So we're going to norm CDF this guy. I'm just going to copy and paste this number so I have it. Okay. Okay, so menu 652 is norm CDF. We want to go from 0.82 to 0.86. Mean is 0.84. Standard deviation is that. Just copied it. And we get 89.5% of the time it's going to be within 2 percentage points. Yeah. And we had ours with a little bit more precision because of what we used for our standard deviation. They used they converted z-scores and they did it in terms of z-scores there, and they did it our way there with a little rounded off number, and they get that number. Ours is a little bit more accurate, I think, 0.956, which would be, we just used the actual value for standard deviation, they rounded. According to the National Center for Education Statistics, 20% of students who recently earned bachelor's degrees were business majors. Imagine taking an SRS of 300 students who recently earned bachelor's degrees and calculate p-hat. Proportion of students in sample who majored in business. Identify the mean and sampling distribution. So the mean is p-hat is 0.2. Does it pass the less than 10% condition? So 300 students out of all the students in the United States who were business majors, that's way less than 10%. So we're good there. So then you would be able to use the formula, which in this case is the square root of 0.2 times 1 minus 0.2 or 0.8 all over 300, I believe. So you get that number, 0.02309. Okay, so identify a mean instead of, so 0.2. I didn't get the standard deviation. Calculate in terms of standard deviation. So first you had to check less than 10%, which it was, and you get that number. So if you want to interpret that in context, the sample proportion of students who recently earned bachelor's degrees and majored in business will typically vary by about 0.0231 from the, this is saying from the mean, from the true proportion of p equals 0.2. So we think that the true proportion is 0.2 there. Describe the shape. So if it passes the NP, the success and failures have to be at least 10. So 300 times 0.2, 300 times 0.8. Those are at least 10 for each of those. So it does pass the condition. So it's going to be approximately normal. That's right. Okay. And then you can answer questions about that if they ask you more by drawing the normal curve, new norm CDF. In 2016, more than 200,000 students took the AP Stats exam. of those students, 14% earned the highest score of 5. So that's pretty elite there. Find the probability that a random sample of 300 students who took the 2016 AP exam would indicate that 15% or higher scored a 5. Okay, so let's think about this. So first, what's the mean of the thing? So find the probability that a random sample of 300 students would indicate 15. So the mean p hat would be 0.14. Is that less than 10%? So the 300 students that were sampled is at least 3,000 people took the AP exam. Oh yes, definitely. So that's less than 10%. So we can prove independence there. And so we can find the standard deviation by getting your calculators out. And you would say square root 0.14 times 0.86 over, I believe it was 300. So 0.02 or 2%. Basically there. So we also have to prove that it's normal before we can use a normal curve. So if we do successes 300 times 0.14, failures 300 times 0.86, those are both greater than or equal to 10, therefore we can use a normal, approximately normal curve to approximate this. So you would get out pencil paper, kind of draw this out, and you can say, okay, 0.14, this would be 0.16, 0.18, because our standard deviations, 0.12, 0.1, etc. We want 15%, which is, sorry, this is 0.818. 15% was right around there, so right about here or greater, scored a high, 5. So what's the chance of that happening? So you would get your calculator out at that point and go menu 652. Lower bound is 0.15. Upper bound is 1 or infinity. 100% is the most, so they'll be fine. Mean is 0.14. Standard deviation is 0.02. We're just rounding it off. And you get 30.8%. Yeah, there you go. And you just go through the progression there. You can see that it really helps to do your homework and practice this to get good at this. So this is like, oh, I can do this all day long. Like this is to go through the checking the conditions and going for it. That's your lesson for today.